right, let's try one more practice. Let's set up the integral of this given function f of x comma y comma z is equal to x times z over the sphere, the filled-in sphere of radius 9. Okay, so first let's just understand the shape in first in our standard xyz coordinates first. I think that'll help us out. That we're talking about x squared plus y squared plus z squared equals 81, right? 9 squared. So we want the stuff inside. Want the inside. Because, yeah, for the filled-in sphere. So I know this should maybe be an inequality for the stuff inside, but I'm going to leave this as an equation for a moment just so that we can see what the upper and lower bounds for z are. So to solve for z, we'll have z squared is equal to 81 minus x squared minus y squared. I'd rather write this as minus quantity x squared plus y squared. Now, if we square root both sides, z is equal to plus or minus root 81 minus the quantity x squared plus y squared. So this is equal to plus or minus root 81 minus, and then here's a convenient place to replace x squared plus y squared with an r squared instead. Okay, so in the picture, there's this sphere. I'll try to draw this real quick here. I'll try to do a good job anyway. So there's this big sphere first, and then I'll draw on the equator, right? So it should look something like this, okay? And then the point is, at any specific, so not necessarily right at the origin, but whatever point you have in the plane here, from here, which you could describe in terms of x's and y's or in terms of r's and thetas, you can go down to find the starting point. Actually, let's make this solid while we're in the object, and at some point you end up leaving the sphere as well. Okay, so the upper and lower values in terms of r and theta, it's really actually only involves r. The value of the angle theta in the xy plane does not end up determining the upper and lower z values. Okay, so the inside integral, the innermost integral, has bounds. We'll set it up like this. So the lower with the minus sign here, that's going to be this lower point, right? So we'll have z goes from minus root 81 minus r squared all the way up to plus root 81 minus r squared. Then we end up projecting. Okay, so you take this sphere here, it should be filled in, and then when you squash this down so it's in the xy plane, every point that's above the xy plane moves down into the xy plane. Every point that's below the xy plane moves up into the xy plane. That should end up providing you this picture, which is a filled-in sphere, filled-in circle of radius 9. Okay, so we have here from this picture 0 less than or equal to r less than or equal to 9, and then theta between 0 and 2 pi. Yeah, so we are in business to set up an integral now. Okay, so to set up this integral, we should have integral sign. Let's leave a little space between the integral signs. The function was x times z, right? The function we were supposed to integrate. Let me scroll to the top and make sure that that's what it was. Yeah, x times z. But we can rewrite that x times z as x gets replaced with r cosine theta. So maybe I'll just point out that that's what happened to x. Z is just still going to be z. No need to change the z because that is a cylindrical coordinate. And then the dv becomes r dz dr d theta. And the z integral being the innermost, we saw the bounds over here. So this should be an integral from negative root 81 minus r squared up to positive root 81 minus r squared. Then r went from 0 to 9, and theta went from 0 to 2 pi. Okay, the integral set up, we're technically done with the question, but this integral can be done, so let's just talk ourselves quickly through how we would do the integral. Let's talk about evaluating this integral. Okay, so z's first. There's really not much work to do because r cosine theta and r, those are all constants as far as z is concerned. So we just have a constant times z. So the integral should involve a z squared over 2. Yeah. So this will copying a lot of the stuff here. 0 to 2 pi, integral 0 to 9. Oh yeah, we're about to do this. So let's just combine the r times r as an r squared, right? So the stuff that is considered constants as far as z is concerned is r squared cosine of theta, and then we have z squared over 2, or a 1/2 times z squared, and we just need to evaluate z at both root 81 minus r squared and at negative root 81 minus r squared, and we still have a dr d theta. So let's clean this a little. Why not? So integral 0 to 2 pi, integral 0 to 9. If we were to plug in, oh look, this is actually super convenient. The square undoes the square root sign. So we would have, we'd end up with actually 81 minus r squared. And then when we take this entire thing and we subtract, let's just write out some details here. Why not? This will just be so copying the 1/2. So the square, let's say, is going to undo the square root sign. So we'll have root 81 minus r squared, and then minus r squared cosine theta times 1/2 times, and then actually due to squaring, we end up with root 81 minus r squared again. Okay, we'll stick that in parentheses, dr d theta. I actually think this is maybe a good place to pause this, because I think we actually have a thing minus itself in the end. That's what the... Oh, we shouldn't write the square roots here. Excuse me. Even if the things didn't cancel out, it looks like they do. I think it's just due to the type of function we were integrating here. The point is, I think here we actually have the integral of 0. Well, I think I have an issue in my own notes from earlier. In any case, I think this is actually a good place to stop this integral. Let's just, assuming that this hadn't simplified, we would have something like r squared. Well, yeah, we'll just write this as a 1/2 cosine theta. Let me just distribute the r squared. 81 r squared minus r to the 4th, I think. Yeah, minus 1/2 cosine theta, 81 r squared minus r to the 4th. I'm just, in case there was a slightly different function here, I'm just trying to write this in a format where integration would be nice next with respect to r. I think this is going to be a good place to pause this. As long as your function is not too wild here, you're going to get something that should integrate relatively nicely. To end the part, what I'd just like to ask is this rather open-ended question for you, an interactive question. And it's really, after seeing what you've seen here, I just want to ask, what kind of three-dimensional shapes, objects, seem to be best to integrate over, written in cylindrical coordinates. This is rather open-ended, so just do what you can with the question.